Hi everyone, welcome to Go Classes. In the previous few lectures, we have seen how to convert English statements into first order logic expression. Okay, so in this lecture, we will see some examples. So I have taken some mathematical statements and now we will see how to convert these mathematical statements into first order logic expression. Okay, so we will write them in first order logic. So let's see this first example. For every number, there is a larger number. Assume the domain is set of all numbers. So how can we do it? For every number means for all x, there is a larger number. There exists a y such that y is greater than x. So this is how we can write it. Okay, very simple. For all x, for every number, okay, for all x, there exists a y such that y is greater than x. So that is the reason for every number there is a larger number. So very simple, because the domain is set of all numbers, so we can say that for every element in the domain there is a larger element. So for all x in the domain there exists a y such that y is greater than x. Okay, let's see the next example. There is a number that is larger than every other number. Okay, and the domain is set of all numbers. So there is a number means there exists x that is larger than every number. So there exists x for all y, we are saying that. So there is a number for all y, we are saying that if this x is not equal to y, then definitely this x is greater than y. So this is the statement. You can notice there is a number that is larger than every other number. Okay, so there is a number, there exists x for all y. If x is not equal to y, then x is greater than y. So this x is basically greater than all the y which are not equal to x. So this is the point. There is a number that is larger than every other number. Correct? Let's see the next. Every positive number is a square. Okay, every positive number is a square. So the domain is set of all numbers. So I can say that for all x, if it is positive, if x is greater than 0, if it is positive, then I can say that there exists a number z such that z into z is equal to x. Correct? See, every positive number is a square. Square means, for example, x is a square. Then I can say that there exists a y such that x is equal to y square. For example, 4, this is a square. Why? Because this is 2 square. For example, 9, this is 3 square, like this. Okay, so the point is very simple. For every positive number, for all x, if it is positive, then there exists a z such that x is equal to z square. So this is how we can write this statement. This mathematical statement can be written in first order logic like this. Okay, let's see the next example. If one number is less than another, then there is a number properly between the two. Okay, so if one number is less than another, so basically for every two elements we are saying, for every two numbers we are saying that for all x, for all y, we are saying that if x is less than y, then what should happen? Then there is a number properly between the two. Then there exists a z such that this z should be between x and y. Okay, so this z, like it's like this. If one number is less than another number, if this x is less than y, then there is a number which is properly between these two. Correct? So like which is properly means this z is basically greater than. Okay, so this I can say this z is greater than x and this z is less than y. So this is what we can write. So there exists a z such that this z is greater than x and this z is less than y. So this is how we can write. Very simple. This is saying that for all the numbers, this is saying if one number is less than another, for all x comma y, this is saying that if x is less than y, then what should happen? Then there must exist a z which is between them. There must exist a z such that z is greater than x and z is less than y. Okay, so this is how we can write this statement. Let's see next example. There are at least two numbers which are prime. There are at least two numbers which are prime. It means there exists x, there exists y. Okay, two numbers must be there. There are at least two numbers. So there exists x, there exists y, such that they must be different first of all. because we want two numbers, at least two numbers, so they must be different, and this x must be a prime and this y must be a prime. So this is how we can write. So very simple, we can say that there are at least two numbers, there exists x, there exists y. Okay, at least two means they must be different, they should not be same. So two different prime number we want. Okay, so this x and y, they should be different, and x should be a prime and y should be a prime. So this is how we can convert. Okay, let's see next example. There are at least three numbers which are prime. At least three numbers we want, at least three. So how can I say? Very simple, there exists x, there exists y, there exists z, such that at least three numbers which are prime. Okay, so x and y and z, they must be prime. So definitely x must be a prime and y must be a prime number and z must be a prime number, and what should happen? They must be different, because see, at least three numbers we want which are prime. So there exists x, there exists y, there exists z, they must be prime and they must be different, they must be different numbers, means x is not equal to y and y is not equal to z and x is not equal to z. So this is how you can convert the given statement. This statement can be written like this. Okay, so this is how we can write. Very simple. Let's see the next example. There are infinitely many numbers which are prime. So there are infinitely many numbers. Okay, so how can we convert this? Infinitely many, how can we say that there are infinitely number which are infinitely many number which are prime? So it's like this. Basically we are saying that for every number, whatever number you take, definitely there should be a number which is greater than this, and this should be prime. Okay, because this is saying there are infinitely many prime numbers, means these prime numbers, they should be infinite. Okay, so for every number there should be a greater number, there should be a greater number which is prime. Okay, for every number there should be a greater number which is prime, for every number there should be a greater number which is prime. Correct? So like this, so I can say that for all x, I can say that there exists a y. For every number there should exist a y, so that this y must be prime. Okay, so for every number there exists a y such that this y is greater than x. Okay, this y must be greater than x, and this y must be prime. So this is how you can convert. Very simple. For every number there exists a greater prime number. This is what I am saying. Okay, for all x, whatever number you take, definitely there must be a greater prime number. Okay, for every number this should happen, that there should be a greater prime number. So then we can say that there are infinitely many prime numbers. Okay, so for all x, for all elements, there should exist a greater number, there should exist a y such that y is greater than x, and y should be a prime number. Okay, so this is how we can convert, this is how we can write this statement. Let's see next example. There is at most one number which is prime, at most one prime number. In the last lecture, actually I have told you, you can just watch the last lecture. There I told you how to convert at least one, at least two, at most one, at most two, exactly one, exactly two. This type of statements, how can we convert in first order logic? Okay, so this I have already explained in the last lecture. The link you can find in the description, or on our YouTube channel you can find all the videos, you can watch them. Okay, so I have already explained how to write at most one. So let's see this. There is at most one number which is prime. So what we are saying, basically we are saying that for all x, for all y, we are saying that at most one means more than one should not be there. Okay, means more than one definitely should not be there. So we are saying that for all x, for all y, we are saying that if they are prime, then they must be same, because more than one we do not want. Okay, so for all x, for all y, we are saying that if they are prime, means if x is prime and y is prime, if they are prime, then what should happen? Then they must be same. So this is the point. Okay, so this is how we write at most one. Okay, whatever statement you have where you want at most one prime number, you are at most one. So how can you write? For all x, for all y, if they are prime, then definitely they must be same. Okay, so this is the statement. There are at most one prime number. Let's see the next example. There is exactly one prime number. So again, this how to write exactly one, at most one, at least one, all these statements I have already explained in the last lecture. You can watch it. There is a exactly one number which is prime. So we are saying that first of all there must be at least one. First of all there must be a prime number, right? Exactly one means not more than one, not less than one, correct? So there must be at least one prime number. There exists a x which is prime, so this x must be a prime, and okay, so this is a prime, this x is a prime, but no other number should be a prime, correct? So there exists x which is prime, and for all y, if y is prime, then this y must be x. So this is the point, okay? So we are saying that there exists a prime number, there exists x which is prime, and for all y, if y is prime, then y is equal to x, correct? So this is how you can write basically. So basically we want to say that only this x is a prime number. Only this x is prime number. This x is a prime number and only this x is a prime number. So this is the statement, okay? So this is how we can write, correct? Let's see the next example. A divides B, where the domain is set of integers. So how can you write? A divides B. So when do we say that A divides B? Let's see in general. In general we say that A divides B. So this symbol means divides, okay? So this symbol means divides. So it means A divides B. A divides B. When can we say that A divides B? Okay, the general mathematics says that A divides B. It means there exists an integer. So we can say that A divides B means there exists an integer such that Ax equal to B. Then we can say that A divides B. For example, 2 divides 4. Why? Because there exists an integer such that 2 into 2 equal to 4. Okay, so there exists x such that Ax equal to B. So this is what we want to write. So A divides B, how can you convert it? Okay, so it means there exists x such that A into x is equal to B. So this is how we can write. A multiplied by x is equal to B. Okay, so this means A divides B, correct? So this is how you can write this statement, A divides B. There exists x such that Ax equal to B. Let's see the next example. X is even number. When can we say that x is even number? X is even number when this is basically multiple of 2. Okay, for example 4 is even number. Why? Because it is multiple of 2. For example 6 is even number. Why? Because it is multiple of 2. Okay, you can notice 10 is a even number because it is a multiple of 2. 9 is not a even number. Why? Because it is not a integer multiple of 2. Okay, correct? So we cannot have any such integer, okay, like this. So because this is not a multiple of 2. So this is the point. Now let's see. X is an even number. So how can you write? Basically we are saying that there exists a y such that x is equal to twice y, correct? So this is the point. X is an even number means there exists a number such that x is equal to twice y, correct? Means this x must be basically multiple of 2, correct? So this is the point. There exists a y such that x is equal to 2y. This means x is a even number, correct? Let's see. X is prime. So basically they are asking how can we write the definition of prime in mathematical logic. We know what is a prime number. Okay, now in mathematical logic we need to write the definition of prime. So we know what is a prime number. Prime number is basically any number which is divisible by itself and 1. Okay, so basically 1 is not a prime number. Okay, so first of all x is prime. It means first of all x must be greater than 1. First of all x must be greater than 1. Okay, and now because 1 is not a prime number, right? So this x is prime, it means x must be greater than 1. And now we can say that if anything divides x, because x is prime, it means if anything divides x, if y divides x, then what should happen? Then this y should be either equal to 1 or this y should be equal to x. So this is the definition. This is what we need to write. Okay, let's see. So x is prime means x is greater than 1, and for all y we are saying that, for all y we are saying that if y divides x, if y divides x, then y should be either equal to 1 or y should be equal to x. So this is the definition of prime number, correct? So very simple definition. The idea, the definition of prime number that we know, we are just writing it. X is prime, it means it must be greater than 1, because 1 is not a prime number, so it must be greater than 1. And for all y, if y is dividing x, then this y must be 1 or this y must be equal to x, correct? So this is the mathematical expression for the definition of prime number. Let's see next example. X is prime. Okay, so this is how you can write, correct? X must be greater. Okay, so this we have already seen. X is prime. Let's see the next statement is this: the relation divides is transitive. So how can we write this in mathematical, in first order logic? The relation divides is transitive. What is transitive? Basically, the relation divides is transitive. It means like this. So if A divides B and B divides C, then what should happen? Then A should divide C. This should happen, correct? So this is what we need to write now. So basically we are saying that for all A, for all B, for all C, we are saying, for all three numbers, we are saying that if A divides B and B divides C, then what should happen? Then A should divide C. So this is the expression. Very simple. Okay, just use the definition of transitive. So this statement is saying that basically if A divides B and B divides C, then definitely A should divide C. So for all A comma B comma C, we are saying that if A divides B, B divides C, then we can say that then A should divide C, correct? Let's see the next example. There are infinite number of primes. Infinite number of primes. This we have already seen. So okay, there are infinite number of prime means for every number, whatever number you take, for every number, there must be a greater number which is prime. There must be a greater number. So this is how you can write. Basically we are saying that for all x, there must exist a y such that, okay, for every number, what should happen? For every number, there should exist a y such that this y must be greater than x and this y must be prime. This we have already seen actually, so just repeating. So for every number, whatever number you take, there must be a greater number which is prime. So then we can say for every number this should happen, for every number this should happen. So we can say that there are infinite number of primes. So for all x, there exists a y such that y is greater than x and y is prime. Let's see the next example. There are infinite number of pairs of primes that differ by the number 2. This is a conjecture actually. This is twin prime conjecture. So this conjecture says that there are infinite number of pairs of primes that differ by number 2. For example, this 3, 5, they differ by 2. Okay. For example, 11, 13, they differ by 2. So these are prime numbers, they differ by 2. These are prime numbers, they differ by 2. So this conjecture is saying that there are infinite number of pairs of prime numbers. This type of pairs, infinite number of pairs must be there such that they differ by number 2. So how can you write? Again, very simple. Okay, basically we are saying that, what we are saying? We are saying that for every number, there must exist some prime number. For every number, what should happen? Infinite number of pairs means for every number we should have a pair, correct? Whatever number you take, there must be a pair. Okay, so there must be a prime number, and the prime this number plus 2 also should be prime, correct? So this number plus 2, that should also be prime. Okay, so like this. So what I can say, for all x we are saying that there exists a y. For all x there exists a y. So let me write it. Okay, let me write it this way. So we are saying for all x there exists a y such that this y must be greater than x and this y must be prime, and this y plus 2 must be prime, correct? So this is the point. See, the explanation is very simple. Let me explain it again. We are saying that for every number, whatever number you take, for all x, we are saying that there must exist a pair. This is what we are saying, because the question is saying infinite number of pairs. Okay, so for all x, we are saying that there exists a pair, means for all x there exists a y such that y is greater than x, and y is prime and y plus 2 is prime. So basically this means that for every number there exists for every number we can say there exists a greater number such that these two are prime. Okay, prime pair exists. For every number there exists a prime pair. Okay, twin prime pair. Okay, let's see. So next example. So this is the point. Okay, so for all x there exists a pair. Whatever number you take, there exists a pair. Whatever number you take, there exists a pair. So for all x there exists a pair. Okay, for all x there exists y is greater than x, y is prime and y plus 2 is prime. Let's see the next example. This is Goldbach conjecture. Okay, so this conjecture says that all even numbers greater than 2. So if a number is all even number greater than 2 are sum of two primes. So how can you write? Very simple. Basically this is saying that for all numbers we are saying that if it is even and it is greater than 2. If it is even, okay, means how can you write? Okay, so for all x we are saying that if it is even, if x is even and x is greater than 2, if x is even and x is greater than 2, then what should happen? Then you can say this x is sum of two primes. Okay, then what should happen? Then there exists a y, there exists a z such that they must be prime. Okay, so such that they must be prime means y is prime and z is prime, and this x must be equal to y plus z. Okay, so this is how we can write. Very simple. Okay, let's see. See, this is saying for all even number greater than 2, means if a number is even and greater than 2. For all x we are saying if it is even number and greater than 2, then what should happen? This x must be summation of two prime numbers. So there should exist y and z. There should exist two prime numbers. There should exist y and z such that y is prime, z is prime, and this x must be y plus z. So this is how you can write it. Very simple. So okay, so these are some examples. I hope that you understood all of them, and if there is any doubt you can ask in the comments. You can ask, or also watch the previous lectures. If there is anything that you did not get, just watch the previous lectures and it will be clear. Okay, thank you everyone.